Welcome to this class on hardware security. So today we shall be starting a new topic. We shall be starting to discuss on what is called as microarchitectural attacks, which basically is kind of the confluence of architecture or computer architecture and its effect on security of ciphers or cipher implementations. So we shall be starting this discussion with a quick discussion about what is meant by microarchitectural leakages. We shall be trying to talk about timing channels in cryptography, which is a very important aspect to understand to realize an end-to-end secured implementation. We shall be discussing in particular about cache attacks and timing channels created using cache memories, and then we shall be talking about the types of cache attacks, and then finally cache timing attacks on AES. We intend to also discuss about cache timing attacks on small table ciphers and their impact on the impact of techniques like parallelization and out of order loading. And finally, we shall wrap up with a case study on a cipher called Clefia, like basically a cache timing attack on a Clefia, which is again a standard block cipher. So first, let us have a quick look on the effect of microarchitectures on security. So computer architecture has been fundamentally designed with performance as a primary design criteria, and security has always been an afterthought. For example, we have various techniques like speculative execution, which is an optimization technique where a computer system performs some tasks that may not be needed. So this essentially has been the basis of several attacks, leading to a very famous attack which has recently been discovered, which is called as Spectre and Meltdown. So this is the reference of this attack, and this basically kind of shook the world and took the world or most part of the world by surprise. And to wrap up, or to quote Bruce Schneier, who is a very famous security expert and security commentator, fixing them either requires a patch that results in a major performance hit, or is impossible and requires a re-architecture of conditional execution in future CPU chips. So this is essentially extremely difficult, because at this point, after so many years of evolution of computer architecture and techniques of how to handle such kind of executions or speculative execution, it is kind of like that we have to go back 20 years. So this essentially makes the entire scenario quite dangerous. So all this happens primarily because even now when we kind of find out or develop a new technique, our primary goal has been performance. So security, right, essentially cannot be an afterthought, and these kind of attacks again and again tell us that we need to have proper design for security criteria. So there are so how do you kind of model microarchitecture? So this becomes extremely complicated because of the fact that when we run our processes on computers, then there are so many complicated things which happen. There are so many complicated interactions that modeling of such kind of attacks becomes extremely challenging and difficult. For example, when we have talked previously about side channel attacks, where our primary focus was like power and electromagnetic radiations, we found that we can actually, although not exactly accurate, but we can essentially fairly model them by methodologies like Hamming distance or Hamming weights of the internal states. On the other hand, leakage, right, when we talk about computers or like computing systems, can be actually a function of several parameters. For example, it could be because of the branch prediction algorithms, it could be because of hyperthreading, it could be your memory technology, it could be your memory hierarchy, it could be the cache memory or the cache memory architecture, and there are so many other things which can be of direct consequence or direct impact on microarchitectural leakages. So our focus in today's talk is primarily on cache attacks, and in particular about the timing channel which is created due to the existence of cache memories. So therefore, right, if we take a little bit of look and try to understand why cache memories create a timing channel in cryptography, so let us try to illustrate this by this diagram. So you can see there are again the two members like Alice and Bob, who are essentially participating in a communication where like Bob essentially is using a cipher, and because of that, right, he uses a secret key. The secret key essentially is embedded in its own computing system, and therefore, right, the idea is that the adversary should not definitely have access to the secret key, because then the entire security collapses. Now we can pretty much assume that the computing system on which Bob is working is a general purpose machine which probably from the von Neumann's model has essentially a look like this. So it is essentially you have got a main memory, you have got a microprocessor, but we know that there is a memory wall, and therefore you can pretty much expect that in order to bridge this memory wall, there is an intermediate cache memory which is essentially tries to apply, appear as a staircase between the memory and the microprocessor. So therefore, right, now imagine that the adversary, right, who is basically observing this channel or the communication channel which is untrusted, has definitely access to the input and the output. But along with it, right, imagine that the adversary also has the capability of very accurately monitoring time and measure time or monitor time. So now the objective of the adversary is, again, like any attacker or most attackers, is to obtain Bob's secret key. And now basically the attacker wants to use this time as a channel or a covert channel for understanding what is the internal secret, and therefore the question is, why is time a channel for information leakage? So if you just take a look back or just remember about our old our classical textbooks in computer architecture, we have all seen this, that if there is a cache hit and if there is a cache miss, then there is a difference in timing. For example, if the data is available in the cache memory, then you would expect that the access time of a particular memory access would be less, whereas, right, if there is a cache miss, then there are more maneuvering which happens, which results in a larger access time, because you access the primary memory or the main memory, which is seemingly much lower compared to your cache memory. So imagine that the attacker is able to distinguish between a cache hit and a cache miss because of the ability to measure time very accurately, and then this ability to understand whether an access is essentially resulted in a cache hit or it resulted in a cache miss can apparently reduce the entropy of the secret key. So, in order to again understand that, let us try to take a look about at a specific type of example which falls into the class of what are called as time-driven cache attacks. So again, like observe that suppose you have a cipher like AES, for example, in which there are different parts of the key. For example, K0 and K1 here are symbolic, or K0 and K4 here are symbolic of two parts of the key. Both of them are getting kind of like XORed with your plain text. For example, K0 is getting XORed with P0, which is a part of the plain text again, and again P4 is getting XORed with the part which is K4, and both of them are creating a virtual address which is say P0 XORed with K0, and here in this case it is P4 XORed with K4. So now imagine that the cipher has been implemented with lot of tables, and I will come to this point subsequently a little bit more details, but imagine at this point that the cipher has been implemented using tables, and therefore, right, you make an access at this table at the location or address which is P0 XORed with K0, and here you make an access at P4 XORed with K4. So therefore, right, the adversary is making two independent accesses. Now if you kind of remember about, for example, the AES structure in which there were 16 parts, like when I talk about AES 128, there are 16 parts of the key. Okay, the idea is that each part of the key is independent, and therefore, right, the entropy is proportional to 16 multiplied by 8, that is 128 bits. That means, right, that K0 or K4 and K0 and K4, they should be two independent components of the key. That means that if I give you the knowledge of K0, you basically have no information about K4 and vice versa. Okay, but now we will see how using a timing channel and like just understanding that whether there is a cache hit or a cache miss can significantly reduce the entropy of the key or the key material. For example, if so again, like the adversary, like in most attacks, has got a control of the input, we assume that, so it can basically send pretty much P0 and P4 and can also observe the timing by using a very accurate timing channel. So now suppose the adversary is able to understand that there is a cache hit by understanding that suddenly like he finds that there is an access time. So what happens is that there are two accesses which happens here. So the first access, for example, happens in this table, right? So therefore this is your access 1. So this is your access 1, and this is the second access which happens here in this table. So these two accesses are seemingly independent. But imagine, right, that the attacker is able to find that the access which happens to the second table takes very small amount of time, and therefore he suspects that it resulted in a cache hit. Okay. So now, like in most of these discussions, right, that we do, we will assume that the cipher starts with an initial cache warming, which means that initially there is no data available in the cache. So I would expect that the first access definitely resulted in a cache miss, but the second one can be a cache hit or a cache miss, and suppose the attacker by its ability to measure time accurately kind of comprehends that there was a cache hit. So that immediately tells us that the address at which the the access had happened, okay. Essentially, right, if I just assume a very simplistic model of the cache, and if I initially assume that there is only one element in the cache line, then I can directly write that the XOR of P0 and K0 is same as that of the XOR of P4 and K4. That means these two XORs are exactly the same. Even if I assume that there are multiple values in the cache line, then as I know that what happens is in the virtual address, the position in the cache line is essentially kind of understood by the lower significant bits of the virtual address. So that means, right, if there is something which goes into a cache line, then I would kind of so let me make an assumption that I am not able to distinguish between what goes into or between the bytes which or between the elements which goes into a cache line. That means, right, I will be able to recover a certain part of the address. So that means I can only tell that in that case, right, that maybe the few bits of the address essentially resulted in the same value. That means what can probably happen in that case, right, that when I find that there is a cache hit, I can probably tell that the XOR of P0 and K0, and if I take the LSB, for example, or few LSBs of depending upon how many for example, right, if there are like 64 bytes, then it may happen that 6 bits are used to kind of index that. Then that means, right, the last 6 bits, that means the 6 LSBs of P0 XORed with K0 is same as that of P4 XORed with K4. Okay, so that means that let me just write 6 LSB, for example, to indicate the least significant bits. Okay, so that means, right, it implies that I am not able to recover the entire address, but at the same time, like definitely few bits of the address. Okay, so that basically, so let us even if I forget this complication right now and just assume that there is one element in the cache line, then I can just write that the XOR of P0 XORed with K0 is same as that of P4 XORed with K4, and therefore I can write that the XOR of K0 XORed with K4 is same as that of P0 XORed with P4. So what does that tell us? That tells us that K0 and K4 are now not independent. That means if I have a knowledge of K0, then I know the value of K4. Okay. So therefore, right, it implies that essentially what it implies is that now if we assume that the entropy of K0 was initially n bits and the entropy of K4 was initially also n bits, that means initially we are at 2n bits of entropy. Now because of this information leakage, this suddenly shrinks to n. Okay. In a more realistic scenario where I consider multiple cache lines, okay, so there what will happen is that suppose initially you had an entropy of 2n, that will reduce to n plus delta. So that delta essentially is because of the fact that in a cache line there are multiple values which I am not able to discriminate. So essentially I will not have information about those bits. Okay, but at the same time, right, definitely there is an information leakage because of this, and therefore that implies that this can be potentially dangerous. Even if there is a cache miss, that means suppose an access takes more time, I can in that case write an inequality where it means that the XOR of P0 and K0 is not equal to the XOR of P4 and K4. Even that is a leakage because that tells us that K4 cannot take certain values, which is also equivalent to the leakage of the unknown key. So therefore, right, in both cases we see even if there is a cache hit or there is a cache miss, there is a potential leakage which we need to kind of take care of. So depending upon different kinds of cache attacks or the different or the presence of cache, there are different types of cache attacks which has been defined. So here is a quick sort of quick nomenclature of some important class of attacks. For example, we have got cache trace attacks, we have got cache access attacks, and we have got cache timing attacks. So let us take a quick look in between them. So the cache trace attack essentially stands for the fact that suppose I do a simulation and I basically somehow for all the accesses that a block cipher makes, I am able to kind of understand whether they resulted in a cache hit or a cache miss. For example, right, if I implement AES and in particular the AES SBox as a table, then that means, right, for example, every round of AES makes 16 lookups or 16 table accesses. So if there are like 10 rounds, then I would expect that there are 160 accesses that the AES is making. or the 160 table accesses that AES is making. So now what I am trying to kind of do is I am trying to kind of do a trace analysis by like measuring maybe that power consumption of the system, and I am assuming that if there is an so suppose like there is a cache miss, then that results in a shoot in the power line. So what happens is that if I observe the power line and I see several accesses, then and suddenly if I get a kind of overshoot, then I reckon that or suspect that is because of a cache miss. Okay. So if I have got this ability, then for all these 160 accesses in AES, I am able to know like the pattern of hits and misses. So what may happen is that the first access is a miss, then I get a hit, then there is a miss, there is a hit, and so on. So like I have got a trace, I have got a history of like whether the accesses resulted in a cache hit or a cache miss. So this class of analysis or this class of attacks, basically what they do is they take this cache trace in as an input, then they take the block cipher and then they make an analysis to understand whether they can use this extra information to retrieve the key. Okay. So these class of attacks are what are called as cache trace attacks. So there is another class of attack which is called as cache access attacks, and probably it is a little bit more common or more well known, which essentially resulted from a work by Osvik, and therefore it can be referred also as Osvik's attack. So what it does is basically it uses a spy program to determine the cache behavior. So it's kind of an attack where we assume that both the target or the victim and the attacker or the spy is essentially co-resident and is working on the same hardware platform. It can pretty much happen particularly because of the advent of cloud and other infrastructure which we often share with our adversaries. So in this case, what happens is that initially the spy makes an access to the microprocessor, so it kind of fills the cache memory with some garbage data, and then it allows the AES to execute. So when the AES executes, it of course makes certain accesses, and that implies that it kind of evicts some locations from the cache memory, and therefore when the spy comes back again and executes, and remember that since the spy is like when the spy is executing, and it can again it remembers the accesses where it originally made, and therefore it can time its own accesses, because so the spy is not really timing the like the accesses which AES was making, but is timing the accesses which it is itself making. Okay. So therefore what will happen is that since these locations where when the spy comes up and if it finds that the time is more, then it will potentially suspect that there is a cache miss, which means the AES has evicted those locations from the cache memory, and therefore it kind of will give us the footprint of the AES execution, where AES executed and where AES did not execute. Okay. And therefore now we can combine this with something that we already saw, that when we basically build those equations of P0 XORed with K0 equal with maybe P0 XORed with K1, or is not equal to P1 XORed with K1, and from there can basically reduce the entropy of the entire AES 128. So therefore this essentially is quite a devastating attack, and these kind of attacks are often called as the prime plus probe attacks. So now there are different variants of, as I said, different variants of cache attacks. There is another very important class of attacks which is called as cache timing attacks, and this is even more powerful because it basically kind of claims that it can potentially work over the network, and essentially therefore can be used to attack a remote server potentially. So this is again like straight from the textbook. We remember that if I ask you that there is a bunch of instructions, and then like what is the execution time because of that, then our textbook tells us that if the access time for the cache memory is th, and if the access time for the cache when there is a miss is tm, and if the number of hits is nh and the number of miss is tm is nm, then the total execution time is obtained by multiplying nh with th, and then we add nm with tm plus some noise. This k stands for some thing which I am not able to exactly model. And now imagine that this is the scenario of the attack. So basically there is a remote server which is running an encryption software, and there is a remote attacker who basically establishes a network. So this could be potentially even by something as common as a TCP network, and then basically sends packets to the server to encrypt, and then when the server sends back the ciphertext, Along with it, it also obtains the timestamp or the time of sending the data and receiving the packet back. That means like it basically tries to do a statistical analysis, or the attacker tries to do a statistical analysis to know what is the time which the encryption took in the remote server. And then it basically tries to kind of do a statistical analysis to retrieve the key from there. So this, as you can see, right, is a quite like a very practical attack model, because apparently, right, it can potentially work on over the network. So as we will see in more details, right, in this class of attacks, we actually make also an assumption. The assumption is that the attacker has an access to a similar looking software or similar looking server, okay, with exactly the same specifications which it has pre-characterized. Okay, so it basically can in that particular target server, it can therefore make a characterization with an example of a known key, okay, and then it basically targets the victim server where the key is not known. So it is kind of similar to the template attacks that we have seen in the context of side channel attacks. So this paper or this work was primarily initiated by Bernstein in a work in 2005, which showed that how we can perform a cache timing experiment. So let us try to understand this with the example of AES. So in AES, as we know that, so in particular AES 128, we know that there are 16 bytes of input or plain text. So what we do is we take one of the bytes, for example, say P0, and I want to obtain the value of K0, that means the first byte of the secret key. So therefore the remaining part, that means the remaining 15 bytes of the key, I make several iterations of them. Okay, so therefore what I do is I initially fix the value of P0, and for the remaining 15 bytes I just make large number of variations. So I probably I make 2 power of 15 choices of the remaining plain text bytes, and then I apply it I apply the AES engine on those plain text, and then I also observe the timing corresponding to each of these encryptions, and then I take the global I take the average of all these encryption times, okay, and then I plot them in the form of a timing characteristic. So what I do is I basically take all the values of P0. So initially suppose P0 is 0, and then I basically make 2 power of 15 variations of the remaining 15 bytes. I get the average timing, I plot that average timing, okay. Likewise, I again change the value of P0 to something else, and then like again I apply 2 power of 15 randomly chosen values of the inputs, keeping this value of P0 as constant, okay, to maybe 1, and then I again obtain an average several timings, and then I take the average of that, okay, and then I plot that. So then what I do is I essentially kind of like pretty much fix P0 to all the 256 values, and then I obtain this graph which is called as a timing characteristic of the 0th byte, okay. Note that when I am observing this timing, in order to remove the effect of noise, what I do is instead of plotting or plotting the average time, I also compute the global average, and then I deduct the global average from that individual average time, okay. So therefore, right, this is just a denoising technique, and therefore we obtain the characteristic of the plain text byte B0, and as written here, we obtain the deviation from the mean time, that means from the global mean time. So it is very interesting to see this timing characteristic. For example, you can see that there are certain bundles, okay, and potentially these bundles are because there are some data in the cache line which are difficult to distinguish, and therefore they have a similar kind of timing behavior. So now what we do is that, again, as you remember that in the cache timing attack model, we assume that there is a target server where you can do a templating process, which means you can fix the key to 0, you can derive a timing characteristic as we have seen, and then now you make a target, that means you do not know the key, and therefore you repeat this experiment, and then again obtain the characteristics. So you will find that the characteristics in both cases are pretty simple, except that one of them is a shift of the other. So if you are able to measure the shift by applying some kind of standard correlation technique, right, and if you correlate these two results, then potentially you get the 0th key byte, because you basically get the XOR of this key, and since this key is held to 0, you actually get the unknown key, okay. So therefore the shift is what we measured, and the shift essentially stands for your unknown secret key, okay. So therefore this is a very interesting attack, and therefore, right, people have kind of tried to analyze why cache attacks work on AES. So for that, right, let us just recollect the structure of AES. This is the structure of AES, and then we have to kind of understand how do we implement AES for software. So, for that, right, we note that this byte substitution is or can be implemented potentially as 16 bytes from a 256 byte lookup table, okay. And in fact, right, you can actually implement using bigger tables, okay. So, if you just take a look into OpenSSL, which is a repository of several cryptographic implementations, and if you look into the implementation of AES, then you will find that it is implemented, or every round is implemented using 4 lookup tables, okay. For example, let the input of the round transformation be denoted by A and the output of the sub bytes by B. Then we know that every byte, like the input byte, is basically getting modified by the S box of Rindal or AES into, say, Bij. So, Aij here stands for the input and Bij stands for the output. Again, as you can understand that I can vary from 0 to 4 and J can vary from 0 to 4. So, NB here stands for 4, and therefore, we have got a 16 cross 16 byte wise organization of AES, as we have already previously seen. So, now if we apply the shift rows, then we know that every byte here gets shifted. For example, this is essentially B0 J plus C0. So, C0 for the 0th row stands for 0, because in the 0th row there is no shift. For the second row there is a shift by one location. So, C1 stands for 1, C2 stands for 2 and C3 stands for 3. So, therefore, right, this column stands for B0 comma J plus 0, that is J. This stands for B1 J plus 1, this stands for B2 J plus 2 and this stands for B3 J plus 3. And therefore, right, if in that way you basically accommodate the shift rows operation, and then you have to perform a mixed columns. The mixed column basically performs on this particular column, and you basically multiply this matrix, which is already pre-known. You multiply with this particular column and you get the values of these, okay. So, this is essentially your output. So, now the question is, right, you can definitely write a code where I do these operations individually, but it turns out that in software it becomes much more efficient if we can implement the entire mapping by lookups, okay. So, therefore, right here what we do is illustrated over in this particular slide. So, you can see that what we need to do is this, because this essentially is nothing but SRD applied on the corresponding input bit. So, SRD stands for the S box of AES or S box of Rindal. So, therefore, right, any byte here like this column, for example, can be obtained by multiplying this column like 2 1 1 1 3 with this byte, okay. So, this is the byte standing for the 0th value or the 0th row, and likewise the second element, and then you XOR this with this column, that is 3 2 1 2 multiplied by this should be 3 2 1 1 1 actually, okay. So, I should multiply 3 2 1 1 here. So, let me correct this. This is 3 2 1 1, okay, 3 2 1 1. So, we basically multiply this column with this byte, and that is essentially shown over here, okay. Likewise, you multiply this column with this byte, and that is shown in over here, and finally, you multiply this column with this byte, and that is shown here, okay. So, note that each of these lookups essentially takes a 256 bit input, I mean an 8 bit input, and results in a 32 bit output, okay. And these mappings can be shown here as 4 tables T0, T1, T2 and T3, and this essentially stands for lookups where the input is 8 bits and the output is 32 bits, okay. So, therefore, it turns out that every table here takes 1 kilobyte amount of memory, and therefore, totally, right, it takes 4 kilobytes amount of memory. So, therefore, the AES in OpenSSL essentially has been implemented using these tables, and that implies that there are 4 table accesses that you are doing per round, okay. And that implies that if you take 9 rounds, remember the last round cannot be implemented in this way, because in the last round there is no mixed columns. So, therefore, right, you are making 4 into 9, that is 36 accesses of various lookups, okay. So, there is a significant amount of cache activity that happens because of these kind of implementations, which can be targeted by the attacks that we are currently discussing. So, therefore, right, I mean, so if you do this, then potentially so if you now take, therefore, you know, like try to execute AES with this 4 kilobyte table implementation and consider 2 different runs of the encryption. So, remember, if I just kind of store that as NT as a total number of accesses, then we know that NT is nothing but the summation of the number of misses plus the number of hits in an access. So therefore, NT is a constant, right, because the total number of accesses that you do to the tables remains a constant for that algorithm. So therefore, what I can do is I can replace NH with NT minus NM, and therefore I can rewrite this equation as NT into TH plus TM minus TH into NM plus that constant K. So if I take two different runs of the encryption, and if I kind of take the difference between these two runs, then this part would cancel because this part is a constant. I will only have an effect on or proportionality on the number of misses. Okay. And what we find is that if you take do these experiments, that means if you take the number of misses and do a frequency plot, you will find that there is a nice distribution of the number of misses, which means that the number of misses varies across execution. And that is partly happening because, like your table is big, and therefore, right, it may happen that, like the entire table, right, essentially is creating this nice distribution, and therefore because of this variation in the number of misses, you actually get varying times, which can be exploited by the adversaries to know whether there is a cache hit or a cache miss, and also to perform like a correlation kind of attack that we see in the case of Bernstein's timing attack. On the other hand, right, it is very interesting to know, so cache attacks, right, we kind of suspect will work because of this kind of varying execution time. What if I implement AES with a very small table, like maybe a 256 byte? That means I just implement the SBoxes table, and the other things I do by computations. If you repeat this experiment, then you can expect that now the number of misses will become a constant, because this table size is now 256, and if you expect for modern caches, right, you will have a cache line size something like 64, then there will be like 4 number of misses that can happen, and therefore, right, as we know that there are several accesses that you are doing, like 36 accesses, that means like 4 will remain a constant. That means every time you do this encryption, you will always get 4 misses, okay, and therefore the variation will go. So for example, if you make a plot now, you will find that around 4 you will get a peak, and there will be no other things that will occur, okay. So the question is, right, can you still do an attack on this, because the encryption time looks like constant, and therefore if you vary, then it seems that the cache attack becomes much more difficult, okay. So now what we will study in the next discussion is that how we can still attack this kind of implementations. In particularly what we shall be discussing is that we shall be trying to look into some modern microarchitectural techniques which actually helps us in doing attacks even in those cases, okay. So that we will take up in the next class, and thanks for your attention.